Good afternoon, everyone. Thank you for the opportunity to speak at this workshop, and I hope to be providing a little bit of a Northern Canada perspective to this workshop. I have been the Unmanned Aircraft Systems Coordinator at the GNWT for 4 years now, but I finished my studies at the University of Lethbridge, so I have a little bit of a unique perspective in terms of flying UAVs, initially in Manitoba in the prairies, going through school in Alberta, and then moving north to Yellowknife, where I'm currently based. So in terms of a little bit of an introduction, I work for the NWT Center for Geomatics, who is basically a shared service across all GNWT departments providing geomatic support. That includes just access to geospatial data, as well as doing mapping and analysis projects, doing lots of data management in terms of vector data and raster data. We also build online platforms. What you see over here is our NWT Spatial Data web viewer, where it's basically the best one-stop shop for geomatics data and being able to create those maps. We provide training, resources, as well as advice. And we do that not just for internal GNWT departments, but for any NWT stakeholders. So the data is used lots by private industry as well, such as the mineral tenure viewer, for example. Just to provide a little bit of perspective to my talk, I just basically pulled up a couple stats, forest-related stats of the NWT versus Alberta. So in terms of what we're dealing with is just north of 60, we have about twice the land mass compared to Alberta, as well as the amount of forest lands as classified as area below tree line. In terms of actual forest inventory and forest industry, obviously Alberta has about 15 to 20 times more happening in the industry itself. When we're just comparing basic economies, about 60 to 70 times larger is the Alberta economy than the NWT's one, and you have about 100 times as many people. So in essence, what we're dealing with is having to manage a forest that is twice as large, but with the population and a tax base based on the population of Medicine Hat. And so that brings a whole bunch of complications with it and challenges. Here's a map showing the area that we currently have inventoried in terms of spatial data from a forest vegetation inventory. So we have the tree line over here, just past over Great Bear Lake, going up to Inuvik, and all of over here is classified as forest lands. But you see that maybe 9% is actually inventoried. So we need to think big scale, even though we're working with drones as well. Now, in terms of the context, a lot of the uncertainties that we're dealing with within the GNWT is overarched by climate change. So here's an example of a map showing the 1948 to 2012 trajectories in terms of temperature. And if you look across Canada, you see that the NWT, it's kind of fuzzy with the projector, but it's just already been a hot spot in terms of temperature changes as well as precipitation changes. And a lot of that comes back to permafrost as well, so the permanently frozen ground that a lot of our infrastructure is built on. We don't have a lot of roads in the NWT. A lot of them are winter roads, so we slowly but surely see our winter road season shrinking. We see, in terms of ecological health and tree productivity, we see drowned forests because the permafrost at the root level is slowly but surely melting, and trees standing in standing water. Flooding as well. In terms of cultural impacts, there's also a very important access to the land in terms of cultural use. And as trees are drowning and permafrost starts to melt, that access can become limited as well. So in response to that, the GNWT released a knowledge agenda, which basically in 4 parts highlights not only our research priorities, as well as just our relationships as Northern government, to Aboriginal governments, to research institutes. So this is almost a one-stop shop document to see where our priorities lay. And part of that, as you will see, is in terms of a research priority, is the use of innovative and emerging technologies, such as drones, as well as other Earth observation systems. Now, this slide has been discussed already in a multitude of presentations in terms of what the value add is for drones. It goes along similar lines as to what has already been discussed. So improve situational awareness and site characterization, reduce risk to staff, especially when you get into site instabilities due to permafrost. It's much better to send a drone over than having staff go through that area. Increase data detail. Even though there's an explosion of remote sensing data available around the world, we still have fairly coarse data in a lot of areas in the NWT. So having a drone available can provide that wealth of information and build that archive as well. And reduce workload and costs relative to that as well. Just to give you a brief example on return on investment, we're dealing with about a $2,000, $2,500 dollars per hour in terms of helicopter rates with 4-hour minimums. So any day you take out a helicopter, it's going to cost you 10 grand. So any chance that you can pop up a multi-rotor would be is a good thing. So in essence, maximizing monitoring, minimizing risk. And here's just an example of the data that can come back, even if it's just an oblique photo, showing some erosion and ponding issues along the likely Canada's newest highway, the Inuvik to Tuktoyaktuk Highway, reaching all the way to the Beaufort Sea. Now, we've discussed 3D data, and that 3D data can definitely tell the story as part of a time series. So here's an example of the Dempster Highway, where part of permafrost thaw can be an example of that can be given through retrogressive thaw slumps, which are basically landslides that just will not stop. It's a continuous conveyor belt of thawed material that is running into the creeks. And what that does is if it reaches a road such as the Dempster Highway, we're trying to fill that with material, but that material will continuously slide downhill and will actually push over creeks and causing instabilities on the other side of the valley. And when we capture that with drone data, we not only have a temporal record of that, but then we also see, in this case in 2015, some minor failure precursors that are being captured. When we went back the next year, the site looked like this. So just in terms of site comparison, here we have one of our co-authors, Robert Fraser at the Canada Centre for Mapping and Earth Observation. He's standing right in here. So these are not small potholes that we're dealing with in managing northern roads. And these can happen, as you can see, on an annual basis. And as part of linking back to data availability, we do have 2011 LiDAR data in this corridor, but LiDAR hasn't been reflown just for mobilization costs and other reasons. So drones at a site-specific scale can provide that wealth of time series data. So since 2015 we started the drone program. So I've listed a couple key steps on that path of enablement. So initially, it really started with a situational awareness in terms of what kind of drones are out there, and what can they do, and provide some low-hanging fruit options to show that use, and get that training and SFOC process started. Then a lot of effort was being spent on gaining that management support, because we're not just trying to implement drones within a single department. We are actively implementing this program for the GNWT wide. So you're dealing with a lot of different departments who may all have different needs, who may all have different priorities and ways of thinking about how to integrate this emerging technology. So a lot of that is based on building support across this large region. Program essentials, it's the recruitment of pilots, it's the documentation, it's the ground and flight schools, getting a policy going in terms of managing expectations among pilots, what they can and cannot do, just be a vehicle to follow the regulations. Tracking systems like we've discussed this morning in terms of pilot logs and flight logs and safety plans and all that stuff. And also program evaluation as well in terms of the metrics that are coming back to define some return on investments and impacts. So right now we're in the 18-19 time period, managing the program, continuously training new people. We've now, for the second year in a row, or at least last year, we renewed our blanket SFOC so we can fly anywhere in the NWT. Again, building partnerships further with Ron's former shop in Guillermo and Rob Fraser at NRCan in Ottawa, and continuously reaching out to new researchers that may have this new type of sensor, for example, related more to methane emissions, and permafrost thaw is directly related to emissions as well, so having a wealth of opportunity to deploy new sensors as well. Now, when we designed our program, we followed very similar steps, I assume, as other folks getting a centralized program up and running. That includes just manuals, standard operating procedures, checklists, and making sure that that is equal among all the different departments so that there's one common approach of flying and operating drones within the GNWT. A couple things are of interest, though, for just in terms of showing some differences. One is that we're really having to tweak our expectations and our processes based on remote operations. We're not just talking being just slightly out of cell phone service. We're talking 200, 300 kilometers to the nearest town sometimes where these drone missions take us. So having to have a totally offline, dependable system is the only way to go. Similar to airspace, we're certainly not as complicated as further north, so that is most of the times that's a blessing. So like I've said, capacity building internally, just defining a training program, and knowing that the further north you go, the more issues you get with compass calibration and those kind of issues. There's a lot of emphasis on manual skills. Like we've discussed this morning, flyaways it can happen, and staff need to be trained to know exactly when to take over on manual control and land it back safely. We have long winters, so a lot of our flight school we've actually managed to just do indoors in gymnasiums. Then at least we can train over the winter period when it's minus 30 outside, and then at least have staff trained up for the next field season. And I don't really see that as a limitation in terms of indoor flight, because it's exactly those permanent manual skills that we emphasize most of. If the drone works well, it can fly an automated path, that's great, but quite often compass issues arise, and that's exactly what we want to train. We have now resources in the Department of Lands and Environment and Natural Resources trained up across a wide range of disciplines, including wildlife and waters, forest management, and me with geomatics. But we're still a fairly small program relative to elsewhere in Canada. We have 16 staff currently classified as pilot in command. But again, we're also a much smaller government entity, as you would commonly find in south of 60. So in terms of demonstrations of operational results, here's one example of a more forest-related application flown a few weeks ago. This is mainly just for project updates in terms of laying out a grid of fire behavior plots and seeing what the contractors completed and if it was up to spec. And this information will be fed back into community wildfire protection plans as well once the prescribed burns are underway. Guillermo mentioned a little bit this morning in terms of our initial work in burn severity. So the 2014 and 2015 wildfire season was extraordinary in the NWT. And right away, because we had access to drones, we did some experiments. So not only looking at how can we take staff potentially out of these burned areas where there's a lot of potential windfall, and if it's at all related to ground observations. And if it is, can we then also use or potentially exploit that drone data and scale it directly up to Landsat? So we've been able to come up with a few models to exploit UAV plots to a much larger area, as is shown here with a 60 square kilometer area, just for an example, in terms of some key canopy parameters. Another component is forest hydrology. Again, we're back at the Dempster Highway, and where we have this interesting pattern called injection ice. And it's in essence a process where we already have the permanently frozen permafrost table, and in the fall, slowly but surely that ground is freezing again. But in essence, it's creating an almost an aquifer, where you have two solid layers and then a road blocking drainage going, in this case, to the left. And what that does is, if there's enough moisture still in that system, liquid moisture, in essence, it raises the entire surface up to 0.5 meter or so, which can induce amazing stresses to the highway itself and the embankment. So again, relating that back to climate change, as we see from the 1960s onward, we see an increase in liquid moisture availability even in the November or October to December timeframe. So these streams are no longer fully shutting down. There is liquid water in there, and there's more and more every year. So what we did was we did some change detection, and we flew twice with the drone, a year being separated. And we took the difference in terms of elevation models to see if we can actually map this injection ice and where this occurs. So here you see an example in pink here, elevations that are between anywhere from 30 to 60 centimeters higher than the year before. And if you look under the mat of vegetation, you see there's pure ice underneath that. And that ice can actually exist for multiple years and actually build onto the next freezing period. Another application that a forest hydrology application we're working on is thermal imaging. A lot of this landscape is very flat, and our engineers have sometimes trouble finding out where the water comes from and where to place the culverts. So we've used thermal imaging captured in October to see exactly where this comes from, where's the coldest vegetation, and making a link to where there's the most likely water paths. Now, we're not just building capacity internally, we're also building external capacity by pre-vetting northern vendors to provide drone services to the GNWT. Makes no sense to have a flexible deployment system such as a drone and then still going through a lengthy RFP process. So we have a supply service arrangement to provide us with key data right away. So one of the more innovating applications in terms of canopy height is looking at obstacle limitation surveys just around the airports. So with a special SFOC, or contractors can actually fly at the runways and look at the obstacles just around it, and with the vegetation growth encroaching, that might actually be limiting a pilot's view, or at least not be within spec. And then the canopy height model can inform where they exactly need to clear vegetation. Another application here is rapid response. So if accidents do happen, was that runway actually in spec? And sometimes those runways are gravel based, and of course with permafrost thaw there are implications of that. So there was actually an accident with a freight plane who had to do an emergency belly landing. Happily, our drone vendor was actually on site and got permission to do a quick drone survey to see what the incident site actually looked like. So we have that as permanent record. Similar with erosion information here in Ulahaktak, far north of the tree line. Now, in terms of wrapping up, I wanted to provide a couple considerations. We've mentioned a little bit about the cost of drones. It certainly only starts with the operational kit. Once you start talking airband receiver, a ground control station like an iPad, ground school, flight school for a few staff, and insurance for just a year. And your $2,000 investment in terms of hardware is actually more like $9,000. And then you have to start looking in terms of your team and your capacity to process the data. So do you have the software? Do you have the workstation available? Do you need georeferencing? And those are all costs associated with that. Do you have experienced staff in your team that can deal with GIS data? Otherwise, you need a specialized program with that as well. Cost of data, just wanted to quickly highlight that there's a cost of increasing detail of data. So just in summer 2016, 720 gigs. If we would follow a similar enterprise backup system as we currently store our vector data at $2 a gigabyte a month, that would mean after a summer season, I would be bringing home and incurring a cost of over $17,000. So that's obviously not a solution. So we are working with particular enterprise raster data management solutions. Metadata is important. How is it collected? And how can other users in your organization actually find that data? So there's a whole bunch of standards and considerations there. So in terms of conclusion and evolution of use, I'm sure we follow a very similar trajectory as other organizations, starting out with low-cost, low-hanging fruit. Multi-rotors depend a lot on collaborations and analysis. And now, 2019, we have a wealth of sensors, a wealth of systems, a wealth of knowledge gained in the last couple of years, and have that internal and external capacity. Thank you.